Pre-AP Calculus, Notes 8.3. This is video 2. These are guidelines to help you solve exponential equations. Guidelines means that if you follow these, you're going to be able to solve lots and lots of problems. But these are not necessarily steps, meaning you're going to have to think and you're going to have to experiment to get good at this. That being said, if you can memorize these guidelines and try to apply them, it's going to get you through many, many problems. If an exponential equation has only one exponential expression, like this one right here, there's one exponential expression right here, the other terms are not. Here are things that you would probably try to do. Isolate the exponential expression, means get it by itself. So over here, if we subtract 3 from both sides, we have accomplished that. Change it to log form. So right now we're in exponential form. We learned about log form in the first section of this chapter. So in log form, we would have log base 2 of the argument equals the exponent. And then it says once you get it to log form, see if you can solve the equation. Well, do we know what log base 2 of 8 is? This is asking 2 to what exponent is 8? And that is 3. 2 to the third is 8. Then we solve the equation. If we subtract 3 from both sides, and then divide both sides by -2, we get x is 0. So let's, here's some other scenarios. If an exponential equation has an exponential expression on both sides, there's other things you can do. If that doesn't work, then there's the last option. So let's see if we can do more of the ones if an exponential equation has only one exponential expression, which this one does. So a rookie mistake would be to try to change this to logarithmic form right now. We can't successfully, or at least meaningfully. We could, but there's lots of people that would do this wrong. We don't want this coefficient for e. Whatever the base is, which is e, we don't want the coefficient of here. 3 is not part of the base. If it was, it would be written like this, which it is not. So we're going to divide both sides by 3. We have just isolated the term that has the exponential expression in it. So this is exponential form, and the guidelines are to change this to log form. So in log form, this would be natural log, base e, of the argument equals the exponent. Now, I don't know what natural log of 4 is, and I don't believe that you would know what it is either, because it's e to some exponent is 4. E is an irrational number, no idea what the exponent is. But that doesn't stop us, or shouldn't stop us, from getting x by itself. I'm going to subtract 1 from both sides. Then I'm going to divide each term by 2. Before I do that, I want to make a point. Writing this as natural log of 4 minus 1, some folks might think that we meant that we're subtracting 1 from 4, which we're not. This is natural log of 4 minus 1. To avoid that confusion, I think it's best if I put this minus 1 in front. It's a -1 plus natural log of 4. And then nobody would confuse that -1 as being part of the argument. Going to then multiply each term by a half. That gets x by itself. It says round to 3 decimal places if necessary. That means we would put this into our calculator. and I would strongly encourage you to type this into your calculator, and I got 193 thousandths. This next one also fits into this category, is that there's only one term that's an exponential. So I just want to isolate that. We're going to subtract 4 from both sides. So it's going to be 2 to the 3 minus x equals 6. And then we are going to put this in logarithmic form, which is log base 2 of the argument equals the exponent. Now, what is log base 2 of 6? That's asking the question, 2 to what exponent is 6? 2 squared is 4, 2 cubed is 8. So it's 2 point something. Who knows what that is? So we'll leave it alone, get x by itself. Going to subtract 3 from both sides. I'm intentionally writing the constant on the left, so I don't think it's part of the argument. Now to get x by itself, we're going to multiply each term by -1. I get 3 minus log base 2 of 6 is x. Direction stayed around to the nearest tenth. If I put that in my calculator, I get 415 thousandths. Looks like this works for all of these. This is the same. Oops, not for that last one. So for this one here, we isolate the exponential by subtracting 1 from both sides, and I got to divide each term by 3. Now if I write this in logarithmic form, it would be a natural log, means the base is e, of the argument equals the exponent. To get x by itself, I simply add 1 to both sides. Put that in your calculator, that's about 2.099. Just want to emphasize, we didn't need a calculator for this one up here because we knew what log base 2 of 8 was. We didn't know what natural log of 4 was. We didn't know what natural log of 3 was. We don't know what log base 2 of 6 is. They're irrational numbers. All right, so in this next one, there's more than one exponential expression. If an exponential equation has an exponential expression on both sides of the equation, or if there are multiple ones, here's what we want to try to do. Get the same base for each term. Let's check this out. Is there a way to get these to have the same base? I would say yes. Just go over the other options. Factor. That usually is going to happen if you have 3 terms. If each side has 1 term, log both sides. Well, that's what we have in this case. So we could actually choose either of these options for this one. I'm going to choose the first option. I'm going to change this 8 to a 2 cubed, because the right side has a base of 2. Power to a power property, this is in the previous chapter. That's going to be multiplying the exponents. One of the log IDs for exponential equations is if both sides, if you have an equation in which you have an exponential on both sides, only one, no other terms, and they have the same base, you can set the exponents equal to each other. So we could say 3x minus 3 equals 3x plus 4. Now it's just the linear equation. If I subtract 3x from both sides, I get -3 equals 4. There's no longer a variable to solve for, so you have to ask yourself this question. Is this a true statement or a false statement? If it's a true statement, you would say there is infinitely many solutions. If it's a false statement, you would say there is no solution. This is a false statement. This is no solution. We get 2 more of these fellas. All right, this one here has 3 different terms. Some of those are exponential and some of those are not. So we are going to be doing, notice it says attempt to try one of these. We're going to attempt to factor, see what happens. And so there are 3 terms. I want to split the middle term and see if I can factor by grouping. So this middle term I'm going to split up. I need 2 terms to multiply to get the first term times the last term. So that would be negative 5e to the 2x. Same 2 terms add to get the middle term, negative 4e to the x. What might those terms be? Well, how about a negative 5e to the x and a plus 1e to the x? If you add those, you get negative 4e to the x. If you multiply them, negative 5 times 1 is negative 5. When you're multiplying with the same base, you add the exponents. X plus x is 2x, so that works. So this middle term gets split into a minus 5e to the x and a plus e to the x. That is splitting the middle term. Now if we group the first 2 terms together, the GCF of that is e to the x, leaving us with e to the x minus 5. GCF of the next group, simply a 1, leaving us with an e to the x minus 5. The GCF of these 2 terms is this e to the x minus 5, leaving us with another factor of e to the x plus 1. If we set each of those factors equal to 0, we're not out of the woods yet. We got to solve each of these little fellas. And then we go back up to the first set of suggestions. If an exponential equation has an exponential expression, well, that's not the right one, has only one exponential expression, you want to isolate it, change the log form, and then solve the equation. So I'm going to add 5 to both sides. If I change this to log form, which would be common log, we figure out what x is. It's natural log of 5. If I do the same thing for this other side, subtract 1 from both sides. Then if I change this to log form, it's going to be natural log of negative 1 equals x. And this presents a problem. This one here is no solution. Why is that? We established on day 1 of this chapter our arguments has to always be positive. Negative 1 is not positive. So the answer to this is natural log of 5 only. So last one, we have, this is quite the mouthful here. We have 2 to the x plus 2 equals 5 to the x minus 3. So let's look back at our options. An exponential equation, an exponential expression on both sides. So option 1, get the same bases for each term. Well, one base is a 2 and one's a 5. We're not going to be able to get those to be the same. Factor. That doesn't seem like it's going to be helpful. If each side has one term, log both sides. Let's try that. We are going to common log both sides of the equation. So this is now going to look like this. Common log of 2 to the x plus 2 equals common log of 5 to the x minus 3. Seems like we just made it a lot more complicated, and we did, but I really don't know how else we could do this problem. Using the power property, I'm going to take these exponents and write them in front as coefficients. That's going to be x plus 2, there's multiple terms, so we got to put it in parentheses, times log of 2 equals x minus 3 times log of 5. Once again, sometimes in math, you have to make things dirty to get them clean. So what I mean by that is I don't know what else to do but distribute this log of 2 to each of these terms. Distribute these log of 5 to each of these terms. You're going to have x log of 2 plus 2 log of 2 equals x log of 5 minus 3 log of 5. Something else we can do is this term right here. This coefficient I can put with the exponent. I can do that with any of these. Keep that in mind. I'm going to do it with this one because I know what 2 squared is. That's going to be 4. I'm going to also do it with this one because 5 to the third is going to be 5 times 5, which is 25. If you get 5 quarters, it's going to be 125. I'm not going to do it with the variables because I want those to chill. So I'm going to move the terms that have the variables on the left. I'm going to move the terms that don't have the variables on the right. In addition to moving this over and moving this over, I change this log 2, common log of 2 to common log of 4. And I changed minus 3 common log of 5 to minus log of 125. I keep saying common log, which you can say, just saying it to emphasize it. But if you just say log, it's implied that it's common log. So common, you don't have to say the word common. So this seems like quite the mess. How is this helpful? Did I make a sign mistake here? I did. We are subtracting this from both sides, which means that I move this to the right, it's going to be negative. All right, so when we get to this point, this is where people usually get stuck. They're like, I didn't know what I was doing, but I got to this point, and now I don't even have a guess of what I could do next. On the left, now you can factor an x out, so we won't have multiple x's. On the right, you could factor a -1 out if you wanted. You wouldn't have to. There's many ways to finish this that are correct. We're basically just trying to get x by itself, but there's some things we could do to make this easier to put into a calculator. For example, log of 2 minus log of 5, we could write as log of 2/5. It's the quotient property. On the right, log of 4 plus log of 25, we could write as log of 500. So we're multiplying the arguments. So to get x by itself, I could write this, probably is about as simple as I could make it. The direction said to round to the nearest 3 decimal places. If you put this in your calculator, once again, I encourage you to actually do that. We should end up with a negative 6.784, I believe. All right, that concludes this video. We have one more in which the equations start out in logarithms and we're trying to solve them.